Hi, this is Tao Lei. I'm pleased to present our paper titled Dynamic Language Splitting in Relational Visual Reasoning. This is a joint work with Vương Lê, Sveta Venkatesh, and Chun Chan at Deakin University, Australia. Our paper studies the problem of visual question answering. The task of visual question answering is that you given an image and a natural language from question about the contents of the image, and you try to build an AI system that can answer the question accurately. From the AI research perspective, the VQA task sit on the intersection between computer vision, natural language processing, machine reasoning, and machine learning. To understand the contents of a given image, we need to use computer vision techniques to detect and recognize objects, as well as the image scenes in the visual contents. While we use natural language processing to help machine understand the meaning of the question being asked. To able to arrive at a proper answer, machines need reasoning capability to infer new knowledge from the information it detects and recognize from the image. In many cases, common sense reasoning is required to answer question. For example, given a question of somebody riding a horse, the question is who riding the horse, and the answer has to be either a person, a man or a girl, but cannot be like a newborn baby or an animal. Last but not least, in practice, the VQA task is usually treated as a classification task, and therefore we need machine learning techniques as well to solve the problem. Reasoning plays a crucial role in visual question answering. My research sets this aspect as the main problem of interest, and to have better clarification of why reasoning is important, I will explain the difference between the VQA system when it needs and when it doesn't need reasoning. Say the object recognition tasks that we usually deal with in computer vision can be formed as a visual question answering task, where the question is what is present in the image, or in particular this example given in this slide, the question can be what is the animal in the picture, and this kind of task this kind of task can be handled with a simple neural network, and it's usually give a trustful answer if being trained on a clean data set, and there's no reasoning needed for this kind of task. How about this kind of question? What is color? What color is the things with the same size as the cyan cylinder? As you can see, that the correct answer should be green, but our network seem to guess the most common color in the image for the answer, which is cyan in this case. And it's also possible that the network suffers from the linguistic bias. However, this might not be the main reason for this failure. And the answer here is that because this kind of question requires multiple step reasoning rather than simply recognizing objects. As a human being, we would first find the cyan cylinder, and then we locate the other object of the same size, and finally we determine its color. So simple feed-forward network doesn't seem to handle this very well. Recall that the reasoning capability is to deduce new knowledge from previously acquired knowledge in response to a query. Based on the general definition of reasoning in the previous slides, reasoning in the context of visual question answering is the ability to chain the relational predicates to arrive at a final conclusion. And with this kind of question, it's essential that a model need to understand the spatial relation in a certain context given by the question. So everything is conditioned on the query. And I will explain more on this later. And chaining also query driven, as how we find the final answer is pretty much depends on how we interpret the question. And in Addison, some predicates in as more important for one question, but it might not be necessary for the other one. And representation of visual objects should be conditioned on the question as well. As you know, there's more variants of there are a lot of variants of object classes. For example, cats are different in size and hair color, and language bindings would stand out the visual representation of a particular object of interest. And our purpose to design a new network is to have a network where everything is end-to-end differentiable. For the approach, we first emphasize that the network we have we work with reason feature instead of read feature, as in many previous work. So read representation is the output of common convolutional networks such as ResNet or VisiNet, let's say. While the reason proposal is the output of the object detection algorithm, where one bounding box represents a possible object detected in the image. And in terms of semantic meaning, the reason proposals and rules have the same semantic abstract level, while this doesn't hold in case of the grid representation. As a result, the reason feature will help to have better interpretive for neural network. Here's the final network architecture that we have proposed. We call it language binding objects graph network, or LogNet for short. We use a faster CNN for object detection, whose output is a bounding box feature. As for the language part, different from many previous work that only make use of the last hidden state of the LSTM path to represent the global feature of the entire question. We maintain the hidden states at its LSTM path at all time steps, and refer those hidden state as linguistic objects or contextual words in the figure. So LogNet is a series of log units that chains together. I will talk about each of the log unit in the next section. And please keep in mind that the LogNet operates on the object level in both visual cues and linguistic cues instead of the pixel level that many other work in the VQA literature has used. And this is the inside of each log unit. It's composed of three components: a visual graph constructor, a language binding constructor, and a representation refinement module. The output of the visual graph constructor is a graph connecting all the visual objects detected from the object detection algorithm, and the edges between visual objects are conditioned on a subset of question words. For example, given a question, what is the blue object in front of the red big block? Early log unit may use some words only. Let's say the blue object, while the other log unit might use the red big block to decode the visual graph. Those language cues are extracted by attention mechanism, and language binding constructor helps build a bipartite graph, as you see here, between the vision objects and the linguistic object. And the bipartite graph will decide how much a word in the linguistic objects affects the representation of visual objects. And representation refinement will help refine the representation of object um, of visual objects based on the information of the objects connected with it in the visual graph. Um, Here is how we build a visual graph. Note Nodes are visual objects, and edges are calculated by the similarity between objects by an outer product as presented here. On the left side is a finger to show the subset of what's in the question that is used by each log unit in our network, and the figures on the right show the visual graph learned by the lognet. As you can see, the network converts after a few log units, so the topology of the graph doesn't change much in later units. The language binding constructor decides how much a word affects the representation of a visual objects. We calculate the widths based on attention mechanism as well. And then we update the representation of visual objects by taking into consideration the effect of language binding. The combined objects representation is simply the concatenation of the visual representation itself and the weighted sum of the linguistic words. Um, so for the node representation refinement, we use a graph convolutional network to refine the representation of visual objects based on the connection with its neighbors. And we also utilize the skip connection trick that allows stacking more layers due to the robustness with gradient vanishing, similar to the bottleneck block in ResNet. And here's some example of our graph as well as the binding. The red connection illustrates the relation between the visual objects, while the cyan connection is slightly, the binding between the language objects and the visual objects. The links are all dynamic, depends on the reasoning step. So for example, we got a question here, the binding. The binding will tell us that we need to look at the color of each object instead of like in the second example, we need to look at the shape of the object instead. So here's the results of our methods. It can be seen that our methods show the advantages of our previous work, especially when we deal with small amount of training data. The improvement is from the object proposal, of course, and the robustness of modeling the relations between objects. As a relation between objects in these datasets is limited, only a small amount of data needed to encode them, and this explains the robustness of our method given a small amount of training data. And even we couldn't beat the state of the art on the challenging IJCAI dataset. It looks like we need smaller amount of training data to reach the same performance, and it reveals that we can make use of data better than previous works. So in this work, I has proposed a method to dynamically chain visual relational predicates conditioning on cross-domain contact information. And the studies of ours is on how the explicit interactions of cross-domain objects helps reason an answer given a complex question. And that's it for my presentation. Thanks for listening.